Southern California Earthquake Center, of course, the USC, and I could spend the whole hour and a half introducing Tom, to the head of the department at MIT for a decade, ran the sketch for almost 2 decades. Now he's launched into all kinds of new things. I'll just say he's going to talk about the Cybershape Project, putting more physics into PSHA.
Good morning. I've got the fortune to be able to talk right after Norma Abrahams's very stimulating talk on how we might combine empirical and physics-based methods to get better PSHA. I'm speaking on behalf of a very large collaboration organized by SCEC, but including people from the USGS, PEER, and other places, to try to use advanced computational methods for generating physics-based models that can be used in PSHA. And the Cybershake Project is sort of our mainline project on this because we actually can calculate full probabilistic seismic hazard models using this computational platform. So it is a high-performance computational platform that can compute synthetic seismograms, very large ensembles of synthetic seismograms, hundreds of millions, required for simulation-based PSHA. We started out in the Los Angeles region, and we've been since then improving the modeling that goes into our understanding of that region, but also beginning to translate Cybershake into other regions, such as Central California. The seismogram synthesis accounts for both source complexity and crustal structure, so we use 2D kinematic rupture models that are calibrated observations and fully dynamic rupture models. We use 3-dimensional seismic velocity models derived from high-resolution tomography and also from a lot of near-surface data. These codes have been optimized. There's been a development of workflow tools that allow us to put together these very large suites of calculations, and we've been able to reduce the computational cost considerably, where it's now feasible to do California size equations. So we're going to show briefly some of the results for Southern California and Central California. We'll soon be moving to the San Francisco Bay Area. There are a number of presentations at this meeting on Cybershake. Following me, C.D. Krause will be talking about the application of Cybershake to the tall building design problem. I will talk just after that in the technical session on more technical details about Cybershake, including the issues that Norm raised on reduction of the unexplained variability in ground motions. But there's a number of other talks that you can see here which are fleshing out some of the work that's being done on Cybershape. And you can just tell from all the names that this really is a very large collaboration. So in places like California, advanced PSH combines the earthquake rupture forecast with ground motion prediction equations to estimate long-term seismic probabilities, shaking probabilities. Both of these components have been refined through comprehensive collaborations that have iterated the models. The USERP model, there's a talk on USERP as I speak. Ned Field is talking about this in another session. Now we're up to USERP 3. SCEC and the USGS have been developing those models. The next generation attenuation project managed by PEER has been improving the GMPEs. But we still know that there are large uncertainties. We just don't have the data to really constrain the earthquake rupture forecasts for large earthquakes or to validate it very easily. Moreover, there's a lot of unexplained variability in the ground motions, as you heard from Norm's talk, with sigma sub t's on the order of 0.6 for the ergodic models, which are associated with the unexplained variability due to 3D effects. So the question we're asking is, what degree can the epistemic uncertainties in PSHA be reduced using constraints derived from these simulations? And this is really the focus of the SCEC program. We have, what we're doing is building on top of the standard PSHA methodology, the simulation methodology. Rob Graves and a bunch of us published a paper in 2011 on the first Cybershake calculations. What I want to mention briefly is the source characterization problem, because we now have simulators that can actually develop earthquake rupture forecasts, and I'm going to mention the RSQ Sim simulator. That stands for Rate State Quake Simulator, developed by Jim Dietrich and Keith Richards-Dinger. This is a very powerful tool because it models the tectonic loading of faults, the spontaneous nucleation and rupturing of faults, as well as the stress transfer that's slip-mediated. When one fault ruptures, it changes the stress on another fault, and that goes into the simulator. What I want to show you very briefly, is not the main subject of this talk, is a new result just now in Press and Science Advances, a team led by PHYS, where we have taken the USURF3 fault model and the slip rates from USURF3, put them into RSQ-Sim, and generated very long rupture catalogs, so on the orders of millions of years, so many, many events. And from that, we can get statistically an earthquake rupture forecast. We can use the GMPEs to then calculate a hazard map, and this shows you the results between the empirical USURF3 model and the physics-based RSQ-Sim model, and they're really quite similar. What's remarkable about this is RSQ-Sim is not using any parameterized statistics. It's just doing deterministic simulations. And so this is the kind of calculation that builds up confidence that the statistical models may have some merit. So what we are going to be doing is actually coupling earthquake rupture simulators to ground motion simulators to have fully essentially physics-based ground motion calculations from which we can derive PSHA products. Now, I label this top row as physics-based simulations in quotes, and the empirical models also in quotes, because as Norm just pointed out, the empirical models really do have a lot of physics in them, and the physics-based simulations really have a lot of empiricism in them. And so we don't expect the physics-based models to replace the empirical models. What we really expect is a melding of the information that we get from both types of, from both approaches into better models. And we have now developed an infrastructure that allows us to make these combinations. So the Cybershake ingredients are the three main ingredients. We first of all have to have an extended earthquake rupture forecast. Obviously, the earthquake rupture forecast, I'm going to be showing you calculations from USURF2. But we have to add to that the conditional hypocenter distribution. Where's the hypocenter? How are they distributed on the ruptures? And conditional slip distributions. How does the variability of slip occur on a rupture? Because those are not specified by the standard ERF. So that's why we call it an extended earthquake rupture forecast. We have to have three-dimensional models of crustal structure that give us the large-scale heterogeneity associated with the crust, but also, very important, the sedimentary basin structures and near-surface properties. And these we have through the SCEC community velocity models that build in these elements. Thirdly, we have to be able to compute hundreds of millions of seismograms, and to do this we're using highly efficient inelastic wave propagation codes. These codes have been developed over the last 20 years or so, and their operation on supercomputers allows us to do the kind of calculations when we combine the codes with a reciprocity-based approach, and I'll show you what that means in a second. We also, of course, have to have the workflow tools that can manage the hundreds of millions of computer runs that go into these calculations. So SCEC has been working on simulation for a long time. Between 2004 and 2010, so 2004 we did the first Cybershape calculations on terascale supercomputers. To 2010, about 6 years later, the efficiency of these algorithms, or the speed with which we could do calculations, increased by almost 4 orders of magnitude. And so by 2010, we were able to do very large simulations, such as this one showing a wall-to-wall rupture on the southern San Andreas Fault. This model has something like 436 billion grid points in space, and the total number of mesh points is very high. We can now do these calculations out to, in this case, 2 hertz. So the models I'll be showing you are restricted in frequencies to about 1 to 2 hertz. We want to make sure these codes are working properly. Verification is very important. And this shows you 3 simulations. This is for the shakeout scenario, done using 3 different codes, both finite difference and finite element codes, on 3 different supercomputer systems by 3 different groups. And you can see that we can get results that compare favorably. We also have to have the 3-dimensional velocity models. This is done by high-resolution tomography. That calculation is actually larger than the Cybershape calculation to be able to do that kind of tomography. This is a model for Southern California that we developed a few years back. You're looking at constant depth slices and velocity variations with depth. The small action goes down to below the crust. And we want to use these kinds of models in our calculations. One of the important aspects of this is the representation of sedimentary basins. So what I'm showing here is one of our earlier models, community velocity model S4, which was developed in the early 2000s using a lot of information on basin structures in the Los Angeles region and also in the Imperial Valley, but not anywhere else. We then developed, or a group actually at Harvard developed a model called CVM H11.9, which has got a better representation of basin structures in Southern California, including expanding into the Santa Barbara region and south towards San Diego. The latest models are these tomographically refined models, and they're beginning to bring in the basin structures throughout Southern California. You'll see that this big blue region right here. This is the Great Valley with a very deep basin structure. We're looking here, I think I said it, at the isovelocity surface at 2.5 kilometers per second. So we think we've got better representations of the sedimentary basins, and we have the ability to compute the seismogram. So the difficulty, of course, is trying to validate these calculations with real data. We just don't have that much large earthquake data in Southern California, but we can use small events such as this one, the La Habra earthquake of 2014, magnitude 5.1 in the Los Angeles region. And what you're looking at is the three models I just showed you, CVMS4, CVMS4.26, and the CVM H11.9. Those synthetic seismograms are shown in red and compared with the actual data in black. These seismograms have been filtered to about 5 seconds period, so this is a long period of motion. And what you can see is that we can do a really good job in terms of kind of wiggle for wiggle matching, including some of the later arrivals. So we believe these models are getting pretty good. They're not perfect. You can see places where there are amplitude discrepancies, but this tomographically refined models tend to explain the seismic waveforms very well. And people like Ricardo Taborda have looked at the comparisons going out to frequencies as high as 1 hertz and showed that, in fact, these models do a better job than previous models we've had in terms of explaining the seismic distribution of seismic energy on the seismogram. We don't have to stick with just 1 or 2 stations. Southern California has hundreds of recording stations. So for this particular earthquake, we've got about 300 good recordings. So we can actually kind of contour up how well we fit the data. The warm colors in these diagrams represent very good fits to the data. Cool colors represent poor fits to the data. And you can see that these, again, these tomographically refined models are giving us very good fits throughout most of Southern California. There's still much more work to be done on the structural inverse problem, but we have made great progress. So how can we use these models in generating synthetics? Well, the problem, of course, is we don't need to do just 1 or 2 calculations of synthetic seismograms. We literally have to do hundreds of thousands in order to properly characterize the various types of earthquakes that can occur among all of the different faults in a region such as Southern California. So in the Cybershape calculation, any fault that has a portion of that fault within 200 kilometers of a station, events that occur on those faults are considered in the Cybershape calculations. And of course, we don't just have one event for a given source. We have to represent many events to sample the variation in the hypocenter, the variation in the slip distributions. So to do this, we use seismic reciprocity. And let me explain why that's so important. There are about 7,000 ruptures in the USERV2 model. We compute about 500,000 rupture variations to represent those variabilities in hypocenter and in the slip distribution. The ground motions need to be calculated at a much smaller number of times, because we only need, in the LA region, on the order of 300 or 400 sites to be able to represent the hazard at a fairly high degree of resolution. We actually use the GMPs to interpolate the Cybershape results. So we could do it by just simulating one event at various sites, simulating another event, and so forth. The problem is that if you have M sources at N sites, you have to do M simulations. And so that would be on the order of 500,000 simulations for a Cybershape model, and we can't do that. Instead, what we do is we turn the problem around and we calculate the so-called strain green tensor for a source located at the site, and then use seismic reciprocity to get the synthetic seismograms by a simple quadrature over each of the sources. And this can be done highly efficiently. This only requires, if we're doing 2 horizontal components, 2 N simulations on the order of 600 calculations as opposed to 500,000. So we get about a factor of 1,000 speed up in the calculation. So the Cybershape platform generates probabilistic seismic hazard models for these very large ensembles, hundreds of millions of seismograms. The one I'm going to be showing you will be using the USER2 ERF. We'll be using the Graves and the Tarka rupture models. These are kinematic rupture models that have been carefully compared with observations and with dynamic rupture models, and the SCEC 3D seismic velocity models. And you can see the distribution of the sites at which these are calculated and the interpolated map. So this is going to be for the Los Angeles region for starters. Here is the Cybershape workflow. It shows you how these models are being combined. We have to sort of grid up the 3-dimensional seismic velocity models into some very dense grids. We have special supercomputer codes to do that. We can then generate the strain green tensors for that particular model for each site in the calculation. We then have to synthesize seismograms. That requires taking the USER2 model and populating the ruptures that model forecasts with the appropriate probabilities, combining them with the kinematic source model for that particular rupture. So we have many rupture variations. Synthesize the seismograms, and then from the seismograms we post-process to get data products such as hazard curves and hazard maps. And so for the Los Angeles region, a complete Cybershape model comprises about 300 million synthetic seismograms. So here's a comparison between a Cybershape calculation using a one-dimensional model. I'm sorry, this is backwards here. So a one-dimensional model, this is the same model we use in the broadband platform, which was discussed yesterday, and you can see this hazard model has very high, we're looking here at 3-second spectral acceleration at 2% in 50 years. This is the Graves of the Target 2010 rupture generator. Here's the one-dimensional result, and you can see these big red stripes along the major faults of the San Andreas and the San Jacinto. These high amplitudes are associated with big directivity pulses propagating up and down these faults that cause very high near-source ground motions. If you compare that with the 3D results, and there are 3 models shown on the bottom, which are for each of the 3 community velocity models that I mentioned earlier, you can see there's quite a bit of difference. In particular, this big red stripe goes away because a lot of that directivity energy is scattered into seismic waves that propagate away from the fault and scattered into into sedimentary basins. So what we see lower near fault intensities because of this 3D scattering. We get much higher intensities in the near fault basins, such as say here in San Bernardino, because of the coupling of the directivity pulse into the basin waves. And we also get, of course, much higher variation in the Los Angeles region in those sedimentary basins. And CB, after my talk, will show how that information might be used in a practical way. We also see lower intensities in the hard rock site. So there's much more variability in these 3D models than in the 1D model. You see more variations in colors. Let's now compare that with NGA models. I'm just going to show the NGA West 1 mean model here, which averages over 4 of the NGA West models. This is the same combination that was used in the 2008 revisions to the National Seismic Hazard Map for California. You can see that the NGA models do represent some of the basin effects, but there's less variability, at least in the blue colors, on this particular model. And in the technical talk after this one, I will talk in more detail about the implications of this for reductions of unexplained ground motion variability. Well, of course, we would like to be able to do better comparisons than just looking at the hazard maps. We'd like to be able to understand how the comparison of, say, the basin effects for the simulations relative to the basin effects in the NGA models. Now, of course, the NGA models have a model-based factorization. You can just factor out the basin term and take a look at it, whereas the 3D models combine all this stuff together, and how do you separate the various effects? It turns out you can do that. We have such a large number of simulations that you can do appropriate types of averaging to bring out the effects of source complexity, directivity, path, and site. I don't have time to go through the details of all of that, but this shows you a comparison between, again, the NGA West 1 models versus a Cybershape model. This happens to be the one with the CVM H11.9, that is the Harvard model. And what you can see, if you look at these basin terms, is that some of the models are, shall I say, don't have high enough amplitude. Some approach the Cybershape calculations. This is the Abrahamson-Silva model, which was, of course, calibrated using simulations, and it does a pretty good job. The other, another important issue is the directivity effects and source complexity effects. This shows you 3 different renderings of the Graves and the Tarka kinematic rupture simulator, one that was published in 2007. It's a fairly smooth model. What you're looking at here is the red patches represent regions of high slip, white or low slip. These black lines represent the isochrons propagating from an epicenter over here, or an hypocenter over here, propagating down the fault. And you can see these isochrons are very smooth, so it's a very regular fault propagation. Graves and Batarka have developed more complex models. In 2010, you can see how this one varies. You can see the isochrons are much more variable. And here's their 2014 model. So as what you're looking at is more and more source complexity. And what we find when we look at the terms associated with directivity is that increasing source complexity decreases the directivity effects. And in fact, these very smooth models give much too large of a directivity effect, but the more complex models reduce that directivity because of the interference, because of the deconstructive interference, and they provide reasonable matches to the observations we have available. So Cybershape hazard products there's many things you can do with the Cybershape model. Of course, we present these in the forms of seismic hazard maps, but underlying those maps are complete hazard curves. We can disaggregate the hazard at any particular site. We can go down, dive into which sources are most threatening, and we can actually get seismograms associated with those sources. So this is all part of the Cybershape database, and it makes it a very rich source of information for engineering modeling. So my conclusions are that we can do this now. We can do simulation-based PSHA feasibly for large regions. We have applied this in Southern California, and we have noted the significant differences with standard ground motion prediction equations. There's typically lower near fault intensities, higher intensities in deep sedimentary basins, and lower intensities in the hard rock areas. And we know that much of the variability, as Norm explained, much of the variability that's not explained by the GMPs is due to 3-dimensional effects, both the path, site effects, and we can show that we can, these accurate simulations should be able to reduce the total unexplained variability sigma sub t by about 1/3. And I'll talk about that in the next talk. That number, which is based upon the simulation calculations, is completely consistent with the numbers that Norm talked about in the plenary talk. So in the next talk by C.B. Krause, there will be more discussion. We'll discuss the problem of the basins in Los Angeles and how Cybershape might be used to improve the estimates of ground motions in the Los Angeles region. We, of course, would like to improve this modeling, and there's many things that we could do to make these improvements, and there's some real difficulties. We need to characterize and reduce epistemic uncertainties. You can start to see how that might be done. We have multiple velocity models, multiple source representations, so we can look at how that variability plays into uncertainty in the modeling calculations. We need to be able to validate these models. We can do this with small earthquakes, but we have difficulty, of course, because this is region-specific. We don't have records for large earthquakes in California. We have to be creative in how we do that validation. One very important possibility is the so-called virtual earthquakes, which can be actually synthesized from the ambient noise field, at least in a weak field approximation. And that is one technique that we plan to use for validation. We need to push to higher frequencies to be able to deal with fault complexity. We need to deal with nonlinearities, both near the fault and also near the surface. We have to be able to, as we push to higher frequencies, to represent the small-scale heterogeneities that are currently not in our tomographic models. That's probably going to be done statistically. And of course, we'd like to extend it to other regions. We have recently done a calculation for the Central Coast region, so we now have Cybershake seismic hazard maps for periods of 2 seconds and longer for both of these regions. And we are in the process of extending this, collaborating with the folks in Menlo Park in Northern California to the San Francisco region. So thank you very much.
I think we're being pretty relaxed about timing here, so does anyone have questions for Tom?
You mentioned RSQC. I'm not sure if it is implemented in the Cybershape project yet.
Yes, it's being implemented. We've actually got hazard curves that have been derived from a combination of RSQ Sim with Cybershape. So this is the first hazard curves that we've produced that are purely physics-based in the sense that they come from simulation models. So we have now hazard curves that have been generated from these deterministic calculations from which we've extracted the stochastic information.
So that means, can we use the RSF friction model, and that would be more representative of probabilistic, right?
I'm sorry?
RSF, like gradient state friction models?
Yes, so RSQ Sim is, RSQ Sim stands for rate state quake simulation. And so it uses the rate and state friction model to model the nucleation of